Okay, thanks very much. Oh, is this working? Yep. So I'm going to talk today about some research that RiskAware has been doing alongside funded work in autonomous cyber defense. And we've been looking at one of the practical issues for deploying deep reinforcement learning agents on real-world networks. I've called this slide introduction, but I haven't gone straight after Jake again. It's probably more of a recap. But anyway, in deep reinforcement learning for autonomous cyber defense, we have this general setup with an environment and an agent. And in autonomous cyber defense, that environment is generally a simulation of a computer network undergoing a cyber attack. The agent will observe the state of the environment and then take actions to defend the network. The environment will then provide a reward signal back to the agent based on the health of the network, how well the agent's defending it. And that reward signal can be used to train the agent, and it can also be used to evaluate a pre-trained agent in that environment. The agent itself is comprised of a policy and a model, and in deep reinforcement learning agents, that model is a neural network. And the policy is responsible for training the model and also selecting actions based on the output of the model. So what problem are we trying to solve? As it says here, many autonomous cyber defense agents would need retraining to defend networks with differing topology and size, which makes them poorly suited to real-world networks. So if we look at the figure on this slide, we can kind of see why. This is actually the agent model from a proximal policy optimization, or PPO agent. So the observation from the environment is the input to the first layer in the neural network. And that observation contains features across all of the subnets and all of the hosts in the simulated network. Similarly, the policy head of the model produces a set of logits across the entire action space, and that action space includes actions on all of those subnets and all of those nodes in all of those hosts in the simulated network. So you can see that the neural network, the number of neurons in each layer, is going to be tied to that specific simulated network. And that's a problem in deployment. You're unlikely to have a real-world network that's exactly the same size and topology as the simulated network. And of course, in the real world, you can have hosts joining and leaving a network, which changes its size and topology over time. So for this research, we've used the Cage Challenge 4 environment. Now, the Cage Challenges are a set of defense industry challenges. They've been gradually getting more complex and increasing in fidelity each year, culminating in Cage Challenge 4 last year. Like all of the environments we've been using on our defense-funded work, it's a gymnasium-compatible environment, so it's compatible with that standard API for reinforcement learning. It's actually designed for multi-agent reinforcement learning solutions. So it has multiple blue agents, they're the defensive agents, defending network segments of differing topology and size. So on the network laydown on this slide, you can see that there are 4 agents defending 4 network segments across 2 deployed networks there on the left. Each of those is a single subnet with 16 hosts in it. And then you have another agent on the right-hand side, which is defending that much larger HQ and public services network. And that's got 3 subnets, each with 16 hosts. The environment also has built-in red agents and green agents. So those red agents they represent the adversary performing the cyber attack. And the green agents represent normal users of the network trying to access services in different phases of a mission. Another thing that makes it good for this research is that it has quite realistic observations, in the sense that they represent host and network intrusion detection system alerts with false positive and false negative events, and realistic actions, in the sense that the different types of actions take different durations to complete. So here we can see some of the information that's in the observation and action space in that environment in Cage Challenge 4. The observation space includes details about the mission phase, the subnets that are being defended, the inter-subnet communication, It's got those malicious process and network events from the IDS. And if you're developing a multi-agent reinforcement learning solution, there's also an optional inter-agent communication block as well. On the action space side, we've got a set of action types. Sleep and monitor is effectively do nothing. Then there are 4 action types: analyze, remove, restore, deploy, decoy, service, that can be applied to individual hosts in the network. And then there's 2 actions concerned with controlling the communication between subnets as well, by setting firewall rules. So to solve the problem that we've set out to look at, we've devised this architecture that we've called TERLA, Topological Extensions for Reinforcement Learning Agents. And the key features about this are that they retain compatibility with existing gymnasium environments, and that they also extend the existing agent model, which means that the extensions can be applied to existing autonomous cyber defense agents. So the TERLA architecture is split into 2 stages. The first of those is a representation learning stage. So the first thing we do is convert the observation into a heterogeneous graph, and then that gets passed through several graph transformer layers before having global pooling in the node dimension. And that gives us a fixed size latent embedding, which represents a sort of aggregated network state. And that provides a fixed size input to the policy learning stage. The policy learning stage is just the original agent model, and in this case, we've extended that PPO model. But the difference is that the policy head of that network now selects actions from a reduced, fixed size, semantically meaningful, and interpretable action space. Those actions are then converted into actions on different targets in the environment using information that's available in the observation, because that's the information that would be available in the real world. Now, we made a decision not to develop a multi-agent reinforcement learning solution because that adds complexity to deployment in the real world. And because of that, TERLA agents aren't going to have any information about parts of the network outside the network segment they're defending. So we're limiting the actions that TERLA agents can perform to actions that can be applied to hosts. So here we can see the heterogeneous graph that the observation gets converted into. There's a schema for that graph on the left-hand side of this slide, and then a kind of simplified concrete example of what it might look like to an individual agent. So you can see we have node types for the mission, for the subnets in the network, and for the hosts in those subnets. So we store properties on them like mission phase, whether the subnet's one of the ones that the agent's defending, and those malicious host and malicious process and network events on the hosts. And then on the concrete example there, you can see that it's, in this example, we're in phase 2 of the mission. There are 3 subnets on the network, the agent's defending the first one of those, and then we can see whether there are any of those IDS events on any of the hosts. The TERLA actions look like this. There are only actually 5 actions total in the action space. Do nothing, and then check for malware on the least compromised host, remove malicious user shell on the most compromised host, re-image the most compromised host, and deploy a honeypot service on the most compromised host. Now, these map directly to those actions in the environment action space, but they map to action types, not specific actions, and then they're targeted based on those malicious process and malicious network events in the observation. So as an example, the most compromised host will be one where there's both a malicious process event and a malicious network event detected on it. Because TERLA agents learn from a latent embedding, which is kind of an aggregated view of the network, we had to implement a couple of additional techniques in Cage Challenge 4 to help TERLA agents to learn. The first of those we called action weighting. And in Cage Challenge 4, blue agents aren't permitted to perform new actions while existing actions are still ongoing. And in fact, the way the environment deals with that is it silently converts any new actions into the sleep action. And then, of course, the agent gets a reward based on having done nothing, even though it thinks it did something else. So we didn't want TERLA agents to learn from that false experience. So we implemented an approach where we don't actually send observations to TERLA agents unless they're permitted to perform an action. We also had to implement reward shaping, and that's because in Cage Challenge 4, all agents receive the same shared reward, and that's part of the multi-agent reinforcement learning challenge. TERLA agents need more specific rewards than that to learn successfully, so they need rewards based on the network segment that they're defending. And the way we implemented that was it was based on the change in health from the previous time step, and it takes into account things like the number of red agent sessions that are running on that network segment, the health of any services being used by green agents, and also whether any of those services are running on a host that is marked as operational technology. So we trained 4 different types of agents, all using the same hyperparameters and all out to 2,000 episodes of Cage Challenge 4. These are training curves on this slide. So we're looking at how the mean episode reward evolved over the course of training. So in the top left, you can see that we trained a set of vanilla PPO agents using the original standard Cage Challenge 4 shared rewards. That's why you can only see one line on this graph, because all of the agents received the same reward, so all the lines are on top of each other, and you can see it converging on a defensive policy as training progresses. We also trained a set of PPO agents with action weighting and reward shaping. That's in the top right. We did that because we wanted to show through evaluation that those techniques in themselves don't improve defensive performance on their own. On that chart, you can see 5 separate lines because it's using shared rewards. You can also see that the agent that's defending the larger network segment with 3 subnets in it gets a lower episode mean reward than the other agents. In the bottom left-hand corner, you can see that we trained a set of TERLA agents, 1 in each network segment. You can see them exploring the policy throughout the training process there. And because we wanted to demonstrate that TERLA agents are agnostic to the network topology and size, we also, in the bottom right-hand corner, trained a single TERLA agent where we deployed the same agent multiple times in each network segment. So the exact same agent is defending the larger 3 subnet network segment as well as all of the others. And you can see that one converges on a defensive policy really quickly, and that's because it's gaining experience across the whole network, across all of those network segments simultaneously. Now, as I said, these are just training curves. So in order to evaluate the relative defensive performance of these solutions, we need to take each pre-trained agent, run it in a deterministic mode, and evaluate it over 100 episodes of Cage Challenge 4, which is the standard way of evaluating in the industry challenge. That's what we can see on this slide. We added a couple of additional techniques in. So far left, you can see no defense against cyber attacks at all. That's the mean episode reward you get if you do nothing and the red agent just goes wild and compromises the network without anyone getting in the way. We also evaluated a random agent. That's the next one along there. Random agent performs lots of actions, occasionally something useful, so it gets a higher episode mean reward than no defensive actions. But of course, any autonomous cyber defense agent ought to produce better results than either of those two. And so third in, you can see the result for the vanilla PPO agents. And that gives us the baseline performance that we want the TERLA agents to achieve, but obviously without the limitation that it would need retraining for a different topology or size network. The next one across is the PPO agents with action weighting and reward shaping, and that actually performed terribly, worse than random. And I'll explain why on the next slide. It's a little bit easier to see. And then on the right-hand side, the two right-hand columns, we've got the TERLA agents and the single TERLA agent. So the separate TERLA agents perform almost identically to vanilla PPO agents, and that single TERLA agent actually performs slightly better. So if we look at the distribution of actions taken by the different agent types over that evaluation, obviously no defenses against cyber attacks was taking no actions. Random agents essentially take all actions the same amount. Fewer allow and block actions because there are actually less of them in the action space. We can see that PPO agents learn to take less restore and block actions because they affect green agents being able to access services in different phases of the mission. And then we can see PPO agents with action weighting and reward shaping effectively learn to do the opposite. That's because those shaped rewards focusing more on cyber defense, and PPO agents aren't able to target those actions effectively. And then we have TERLA agents on the right-hand side, the final two columns, and you can see that they manage to do more restore actions than any other type of action, but because they can target them effectively, they don't incur those penalties. You can also see that TERLA agents perform less actions overall than the other agents. So in conclusion, we've shown that TERLA agents are generalizable to networks with different topology and size without the need for retraining. We've shown that the extensions can be applied to existing autonomous cyber defense agents, retaining defensive performance in the example we've tried anyway, and retaining compatibility with gymnasium environments. And we've shown that actions can be applied more efficiently than with traditional agents, using only observable security events that would be available in the real world. Finally, where do we want to go next with this? We'd really like to apply TERLA to existing autonomous cyber defense agents from DSTL's ARCD and DARPA's Castle research programs, so that we can see whether we can achieve the same benefits in independently developed architectures. We'd like to look at TERLA's ability to address the challenges associated with very large action spaces in large-scale networks, if we can find an environment that's designed for stress testing scalability. And of course, we'd like to evaluate TERLA in any future cage challenge environments as the fidelity and complexity increases. And then finally, I think it would be really interesting to do a prototype deployment in an actual emulated network with a real IDS, using TERLA just as an advisory system to investigate human AI teaming, because I think that's going to be the first stage before we get to fully autonomous cyber defense.